Sections 8.1 and 8.2 are the basis of hypothesis testing. All of Chapter 8 is about testing hypotheses to state whether or not there's enough evidence to support a claim that's being made. We're constantly confronted with people making claims about politics, claims about a product they're trying to sell, claims about a particular belief that they have, maybe a hot button topic such as abortion or gun control. It seems like folks are making claims all the time, and we need to be able to decide who has sufficient evidence to support their claim and who does not have sufficient evidence to support their claim. Perhaps we're talking about a pharmaceutical company trying to manufacture a new drug that helps with migraines, and they make the claim that people who took this drug on a daily basis had a 75% decrease in the number of migraines they had in a year. Well, we need to know how to determine if there's actually enough evidence to support that claim. So hypothesis testing is a scientific procedure, just like biologists and other scientists use the scientific method as an established protocol for conducting scientific experiments. Hypothesis testing is an established protocol for testing the validity of a claim. In statistics, a hypothesis is a claim or statement about a property of a population. We are going to restrict our hypothesis test to talking about proportions and means. There's another section, hypothesis testing on standard deviation, that we're just not going to talk about, but you could. A hypothesis test is a standard procedure for testing a claim about the property of a population. So you make a hypothesis and then you run a hypothesis test to either prove or disprove or say, hey, we don't have enough information to do either one. The main objective of the chapter is to develop the ability to conduct hypothesis tests for claims made about population proportions or population means. Examples of hypotheses that can be tested, the Genetics and IVF Institute, we've been talking about all semester, claims that the XSORT method allows couples to increase the probability of having a baby girl. Now, without any kind of procedure, roughly what's the probability of a baby being a girl? About 0.5 or 50%. The Genetics and IVF Institute claim that with their procedure, P is greater than 0.5 for having a girl. A newspaper headline may make a claim that most workers get their jobs through networking. Most would mean what proportion? Anything more than 0.5. So the claim would be that the proportion of people who get their jobs through networking is greater than 0.5. Medical researchers claim that when people with colds are treated with echinacea, the treatment has no effect. The FAA claims that the mean weight of an airline passenger, including carry-on baggage, is greater than the 185 pounds which was used 120 years ago. Not 120, there weren't planes 120 years ago. Just 20 years ago. It's got me thinking about Kitty Hawk now. I don't remember when that was. When new equipment is used to manufacture aircraft altimeters, the new altimeters are better because the variation in errors is reduced so that the readings are more consistent. What does that make you think of? The variation in errors is reduced. Which population parameter is that referring to? The standard deviation. All right, the standard deviation is reduced. When we were talking about the thermometers, which measured, we're supposed to measure 0 when put in ice water, we said actually they may measure 0.001 or 0.999, but the less variation there is among those readings, then the more precise the thermometer is. I'd rather my pilot's altimeter be precise than a thermometer in an ice bath be precise. It's important to understand that when a hypothesis, which is a claim, is stated and a hypothesis test is conducted, there are three possible outcomes. You can say there is enough evidence to support the claim, or you can say there is enough evidence to reject the claim, or sometimes you just have to say there's not enough evidence one way or the other. Not enough evidence to support or reject the claim. So our conclusion for each hypothesis test will begin, we support the claim, we reject the claim, or there's not enough evidence, but then we want to restate that in a way that it would make sense to a person who's not in a statistics class. We may say, if we find that whatever the clinic was, IVF Institute's claim is wrong, their procedure is really not working, we wouldn't just say we reject the claim. We would say there is enough evidence to suggest that this procedure does not increase the likelihood of having a baby girl. That would make sense to somebody whether you were in a statistics class or not. Note that not having enough evidence to support the claim doesn't mean that you've disproven it. If you have a medical procedure and the manufacturer, the pharmacist is claiming that the medical procedure is effective, if we reject the claim, make sure I'm saying that right. No, I'm sorry. If we say we don't have enough evidence to support the claim, that we don't have enough evidence to reject it either. Sometimes the best you can do is say, you need to go back and conduct some more research, get us some more data, because we really can't say anything about this claim. It's inconclusive. All right, so for the following claims, make a decision about the claim, use only the rare event rule and the subjective estimates to determine whether the events are likely. Let's say somebody's in Las Vegas flipping a coin. I don't know if they do that in Las Vegas or not, but this person is saying, hey, this coin is not fair. It favors heads. So to conduct an experiment, somebody flipped a coin 100 times and got 90 heads. Do you think that claim is supported, supported, rejected, or not enough information? I would say 90 out of 100 heads, that is so unlikely to occur that this person's probably right. The coin is not fair. So the conclusion is support the claim that the coin favors heads. What about this one? Movie patrons have IQ scores with a standard deviation that is less than the standard deviation of 15 for the general population. I don't know who would make that claim or what they have to gain by it, but somebody made the claim movie patrons have less deviation among their IQs than the general population does. So a study was conducted, a simple random sample of 40 movie patrons result in IQ scores with a standard deviation of 14.8. Would you say that that supports their claim or rejects their claim or doesn't really give you enough information? Well, but remember the magic number 30? If it's normally distributed, which we know that IQs are, then it doesn't even matter if they use less than 30. But they've used more than 30, and we know IQs are normally distributed, so sample size is not the problem there. If the person tested 40 movie patrons and their standard deviation, sure enough, was less than the general population of 15, would we go, hey, you're right? It's really close. There's not enough evidence to support that claim. That's just not very different from 15. So that's all you could say, just not enough evidence to support that claim. If you want to go back and randomly sample another 100 people, and it turns out their standard deviation is maybe 13, then you can support your claim. But 14.8 is just not enough difference to make that claim. Components of a formal hypothesis test. Now, the things that I changed about Section 8.2 notes, I tried two things. I tried to look at the great big picture and break it down into 3 parts, because last 2 semesters the 3 parts weren't clear. The other thing I did was worked more examples earlier into the show. You know, instead of talking for an hour and then doing some problems, we're getting to practice each concept as we talk about it. So here are the 3 big ideas, 3 big components of a formal hypothesis test. The beginning is state the claim and identify the null and alternative hypotheses. You don't know what that means yet, and that's okay. We'll refer back to this slide. But the beginning is state the claim, identify the null and alternative hypotheses. The middle is calculate the test statistic and its p-value, compare the p-value to the significance level alpha. Well, we have talked about significance level alpha. The rest of that doesn't make any sense to me yet. Don't worry about it. The end is to state the initial conclusion. The initial conclusion will be reject or fail to reject the null hypothesis, but that only makes sense to somebody in a statistics class. Your final conclusion will be, there's enough evidence to say the IVF treatment does not increase your chances of having a baby girl, or does increase your chances of having a baby girl. But the final conclusion has to be in terms that anybody would understand, whether they had ever taken a statistics class or not. Reject the null doesn't make sense to most people. It's going to make sense to us. All right, here's what I mean when I say the beginning is state the claim and identify the null and alternative hypotheses. The null hypothesis, the symbol for the null hypothesis is H with 0 as a subscript. The word null, nothing, makes you think of 0. So the null hypothesis is H sub 0. It's a statement about that the value of a population parameter is equal to some claimed value. If we were trying to say the IVF procedure didn't work, that the proportion of girls, even with the procedure, is still 0.5, then P equals 0.5 would be our null hypothesis. The null hypothesis always says P equals something or mu equals something. It has no inequality symbols in it. We test the null hypothesis directly, and we either reject or fail to reject the null hypothesis. That'll be the only 2 things we say about the null hypothesis. We reject it or we fail to reject it. We never accept it. That'll make more sense later. The alternative hypothesis, there are 2 primary notations used for the alternative hypothesis, and unfortunately throughout this slideshow, because I did it at sometimes or several times, the alternative hypothesis, sometimes I've used H sub A being for alternative, but sometimes I used H sub 1. Either one of those is the alternative hypothesis. It's the statement that the parameter has a value that somehow differs from what you state in the null hypothesis. If your null hypothesis is P equals 0.5, then your alternative hypothesis may be P is greater than 0.5, or P is less than 0.5, or just P is not equal to 0.5. But the alternative hypothesis is never going to just be equal. It's going to be less than, greater than, or not equal to, which is what the next little bullet says. All right, we're going to practice this. Let's go through this little flow chart and then practice identifying the null and the alternative hypotheses. First, you have to identify the specific claim or hypothesis to be tested and express it in symbolic form. You may write, the claim is that P equals 0.5, or the claim may be P is greater than 0.5. But write it in symbolic form means use P for proportion or mu for mean, and then state whether someone is claiming the mean is greater than, or the mean is less than, or equal to. What is the claim? You have to know that first. Second, you give the symbolic form that must be true when the original claim is false. So, if the claim by IVF is P is greater than 0.5, what would be true if that is false? We're talking about two subsets, something and its complement. If the claim is P is greater than 0.5, what's the complement of that? P is less than or equal to 0.5. So you identify the claim, and then I like to call it the anti-claim. But I made that up. That's not in the book. You identify the claim and its complement. And then of those two expressions, you let the alternative hypothesis be the one that doesn't include an equal in any way, shape, or form, so that the alternative hypothesis just has less than, greater than, or not equal to in it. And then you let the null hypothesis be the symbolic expression that the parameter, whether it's proportion or mean, equals something. Null hypothesis is always going to have an equals in it. Alternative hypothesis is always going to have less than, greater than, or not equal to in it. Correct. Correct. No, the claim can be P is greater than, but that's not the null hypothesis. Null hypothesis always has to be equals. And you see the reasoning behind this as we go along. You may be thinking, who cares what the null is and what the alternative is? Stating your hypotheses correctly is the most important thing in determining whether there's enough evidence to support a claim or reject a claim, or whether you have to say not enough evidence one way or the other. If you don't have your hypotheses stated correctly, you're quite likely to interpret what the calculator tells you incorrectly. All right, so let's practice. This one's all typed out for us, and then I have some for us to practice. Consider the claim that the mean weight of airline passengers is at most 195 pounds. What population parameter does our claim refer to? Mean. It's not talking about a proportion. It says mean weight of airline passengers. So the claim is that mu, the mean weight, is, what does at most mean? Less than or equal to. Less than or equal to. So the claim is that mu is less than or equal to 195. The complement of that is mu is greater than 195. Which one gets to be your alternative hypothesis? The one that does not have the equal to. You never have an equal to in your alternative hypothesis. So this is going to end up being the alternative. Mu is greater than 195, and I have that typed on the next slide. The alternative hypothesis is going to be mu is greater than 195. The null hypothesis will be mu equals 195. The null hypothesis always has to say plain old equals. I don't like to think of it as dropping. We're not dropping it. We will come back to it. But for right now, do it because I said so. And then later, and then later it makes more sense why. All right? So the alternative hypothesis can never have an equals in it, not the equal sign or the equals under a less than or greater than. It must be just greater than, less than, not equal to. And the null hypothesis is always plain old equal to. Now note that the original claim was that mu was greater than, or excuse me, was that mu was less than or equal to. Well, that didn't end up being the alternative or the null. Don't worry about it yet. All we're doing now is practicing using that flow chart to identify the null and the alternative hypothesis. And then Liz will go back to, well, what happened to the less than or equal to? All right, here are some problems. We'll see if we can do the same thing as that previous example. These problems are straight out of the homework. This is exactly what the problems in the homework will say. Identify the null and alternative hypotheses, examine the given statement, and then express the null hypothesis and the alternative hypothesis in symbol form. Be sure to use the correct symbol, mu, p, or sigma for the indicated parameter. In other words, if you're talking about a proportion, use p. If you're talking about a mean, use mu. If you're talking about a standard deviation, use sigma. For every one of these, don't skip the first two steps. Before you jump in there and say what the claim, or excuse me, what the null and alternative hypotheses are, you need to write the claim and what makes it false. What is the claim here? The proportion of people aged 18 to 25 who currently use illicit drugs is equal to 0.20. How do you say that symbolically? We're talking about a proportion, not a mean or standard deviation, so we're going to use a p. And this claim is that p exactly equals 0.2. It's not greater than 0.2 or less than 0.2. It's exactly equal to 0.2. Anytime you claim something is exactly something, you're probably going to be wrong. There aren't a whole lot of things that are exactly anything. Well, that's not alternative yet. That's what makes the claim false. The claim is false if p is anything other than 0.2. You have to write those two down so that you can look at them and say which one does not have an equals in it. False if p is not equal to 0.2. So that is your alternative hypothesis. And what is your null hypothesis? P equals 0.2. The null hypothesis always has plain old equals in it. Now, in this problem, it turns out that the claim is the same as the null, and the alternative is the same as its complement. That's not always true. If it was always true, then we wouldn't write down this middle step. But that's not always true, so it's very important to write down the claim and its complement before you try to identify your hypotheses. Number 12, the majority of college students have credit cards. Are we talking about a proportion, a mean, or a standard deviation? Majority means what? Proportion is greater than 50%. More than 50% of students have credit cards. That's another way of saying that sentence. So what's the claim? That's exactly it. P is greater than 0.5, because that's what majority means. It's not equal to 0.5. Exactly 50% wouldn't be a majority. It's got to be greater than 0.5. That's false if what? And not only less than, but also equal to. Make sure you give the whole complement. P is less than or equal to 0.5 is the complement of P is greater than 0.5. So what is your null hypothesis? Excuse me, give the alternative first. What is your alternative hypothesis? The one that doesn't have an equals in it. P is greater than 0.5. And what's the null hypothesis? Null hypothesis is easy. It's always equals. Now notice that in number 10, the claim was the null hypothesis. In number 12, the claim is the alternative hypothesis. You can't memorize it that way. You have to write down the claim and its complement, and then stick with the rule. The one without the equals anywhere in it is the alternative, and plain old equals is the null. All right, number 14 says the standard deviation of daily rainfall amounts in San Francisco is 0.66 centimeters. What's the claim? It says, it didn't say, sigma. Yeah, it says standard deviation. So sigma equals 0.66. And that's false if what? If it's anything else. P does not equal to 0.66. I wrote sigma and said P. I'm sorry. You're right, sigma. So what is the null hypothesis? It's always plain old equals. What is the alternative hypothesis? The one of these two that didn't have the equals in it. Sigma is not 0.66. It really is better to write down the alternative first. The alternative is always one of these two. The null may not be either one. Like here, the null was P equals 0.5. That wasn't the claim or the complement. And number 16 says the mean weight of plastic discarded by households in 1 week is less than 1 kilogram. What's the claim? Is it P? Mu, the mean weight. And I may have just heard you wrong, but mu is less than 1 kilogram is the claim. That's false if what? Not only greater, but greater than or equal to 0.1. So what is the alternative hypothesis? It's got to be one of these two. It's the one that doesn't have the equals. The alternative hypothesis is always, always, always either the claim or its complement, whichever one doesn't have the equals in it. So here it would be mu is less than 1. And what is the null hypothesis? Always equals. Now, it is quite possible that you're going to leave here feeling like somebody had your brain scrambled for breakfast. Go home and watch the video again. I'll have it on iTunes. I wish I could do it before I left, but if I don't get it before then, it may be tomorrow morning before I can get it on iTunes. If it doesn't make sense to you when you leave here, or if it does make sense to you when you leave here, but you don't try the homework until tomorrow and you've forgotten it all, Watch the video. That's the purpose of me taping. All right, let's go back to the slideshow. We've practiced the beginning. Remember what the beginning was? State the claim and identify the null and alternative hypotheses. We've done that. So the middle. Calculate the test statistic and its p-value. Compare the p-value to the significance level alpha. That doesn't make a bit of sense right now. We have to talk about what a test statistic is, what a p-value is. We have already talked about significance levels. The test statistic for a sample statistic is the number of standard deviations that it lies from the population parameter. What word pops in your head, or what phrase pops in your head when you see the number of standard deviations from the z-score? We're finding a z-score or a t-score, depending on whether we know the population standard deviation or don't know the population standard deviation. All right, but we're finding out how far something is from the mean, or how far something is from the population proportion, or from the population standard deviation. The test statistic is just how far away from the whatever it is. We will use the calculator to find the test statistics for sample proportions and sample means. You don't have to memorize any formula. There are formulas in the book. I think I decided not even to put them in the slideshow. I'm just going to show you how to get them on the calculator. For example, let's consider the claim that the XSORT method of gender selection increases the likelihood of having a baby girl. Preliminary results from a test of the XSORT method of gender selection involved 14 couples who gave birth to 13 girls and 1 boy. What does your gut say? Does this procedure seem to be working, or nah, not really? Heck, if you got 13 out of 14 girls, that's not likely to happen by chance, so something's going on. Switch to one I can write on. Preliminary results are that 14 couples gave birth to 13 girls and 1 boy. State the null and the alternative hypotheses. Before you can state that, you have to state the claim. What is the claim that the IVF Institute is making? All right, you got to give me something other than a pronoun there. What population parameter are we talking about? A proportion, a mean, or a standard deviation? A proportion. All right, so the claim is that the proportion of girls is greater than 0.5. That is false if what? All right, and the way that you would say not greater than is less than or equal to 0.5. So what is the alternative hypothesis? And notice here I used H1 instead of HA throughout the slideshow. Just get comfortable with both of those. What is the alternative hypothesis? The one that doesn't have an equals in it. P is greater than 0.5. What is the null hypothesis? It's always plain old equals. What is P for this sample? How would you find the proportion of girls in this sample? Yeah, 13 out of 14. That's how you find a proportion. I don't think I have that written down. Somebody give me. All right, give it to me as a decimal, and let's go ahead, give me 4 decimal places. Okay, did I understand you correctly? Okay. This sample was almost 93% girls. That's way more than you would expect by chance. The mean, without any kind of procedure, would be 0.5. And in this sample, the mean is way out here at 0.9286. Now, we don't know how to use the calculator to find the z-score yet, but let's play like we did, and we did it on the calculator, and that z-score comes out to be 3.21. That's more than 3 standard deviations from the mean. Is it likely or unlikely to get something more than 3 standard deviations from the mean? Highly unlikely. All right, so a z-score of 3.21 is unusual. Thus, it would be unusual for a sample to have a proportion of 93% of the girls if the treatment was making no difference. I think that's all we needed to say on that problem. Let me go to the next slide. Yeah, that was all we needed to say. Just this is the concept of a test statistic. The test statistic tells how far away from either the mean, the population proportion, or the population standard deviation a given sample statistic is. Yes, or it could be P for population proportion. All right. The critical region or rejection region is the set of all values of the test statistic that would cause us to reject the null hypothesis. The critical region can be in the left tail, the right tail, or both tails of a distribution. We're going to have to think hard about that. I don't want to switch back to Elmo right here, but if you drew the little picture that I did beside the last slide with proportion equals 0.5 in the middle and proportion equals 0.92 way out in the right end, we would, let me think before I say that. We would say something is unusual if its proportion is more than how far from the standard deviation, not standard deviation, but from the population proportion. If it's more than 2 standard deviations, so 2 standard deviations in that case would be our critical value. The critical value, the critical region is just shade everywhere such that if your test statistic falls in this region, Miss Regina, your face is hilarious. let me do Miss Regina for you. I think I might be dying, or I think I might be already dead and gone the wrong way. Hang in there. It gets better. No, it's not going to get worse. Some things take a long time for me to make your light bulb come on, which is basically my job. I'm a light bulb engineer. It takes a long time for us to even establish a foundation on which you can build a framework that makes your light bulb come on. Sometimes you just have to hang with me a few minutes. And then by the time you get to the end, you go, oh, is that all? Why didn't you just say that to begin with? Well, I couldn't say that to begin with because you didn't know any of the words to begin with. We're getting the words now. The critical region or rejection region is the set of all values of the test statistic that would cause us to reject the null hypothesis. It could either be the left tail, the right tail, or both tails. We need pictures. That first picture, let me see if there's anything else. Yeah, the first picture is the picture that you would draw for what is called a left tail test. A left tail test is when the rejection region is in the left tail. If you get a test statistic that's anywhere out there in the blue region, you're going to reject the null hypothesis. The middle picture is that of a right tail test. The rejection region is in the right tail. If your test statistic lies anywhere in that blue area, you're going to reject the null hypothesis. And then the third picture is called a two-tail test, when you're going to reject the null hypothesis if your test statistic is less than something or greater than something. And then the word we have seen before, the significance level alpha, is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. I tried my best to leave that sentence out, but then you can't do the homework. So we got to think hard about critical significance level. Just like with confidence intervals, I said, I want a 95% confidence interval. You immediately knew alpha was what? 0.05. All right. Or I want a 90% confidence level. That means you know alpha is 0.10. Same thing here. It's the probability that even if the null hypothesis is true, we would still get a test statistic in the rejection region. Basically, it's the chance of a false positive. The null is going to be true, but we're still going to reject it. What's the probability of that happening? It all goes back to how confident we want to be in whatever statement we make or whatever conclusion we draw. All right, biggie of the day is p-value. We have a little p for, now what is our symbol for sample proportion? Sample proportion, not sample mean, sample proportion. With a hat on it. P-hat. Remember, p-hat is the sample proportion. P no hat is the population proportion. Now we have a capital P, the p-value. That has nothing to do with the other two. Oh, I didn't make this up. The p-value is the probability of getting a value of the test statistic that is at least as extreme as the ones representing the sample data if the null hypothesis is true. What the heck? Let's think about it. For a left tail test, that means the critical region's in the left tail. Let's say I find out the test statistic, maybe that z-score we had for the XSORT method a minute ago, z is 0.32. Wait, that's positive, so it'd be to the right. For some other example, we may have a test statistic being negative 0.3. If we decide to reject the null hypothesis, if the test statistic is anything less than negative 0.3, then the p-value is the probability that something's going to be less than negative 0.3. For a right tail test, we're going to reject the null hypothesis if our p-value, if our test statistic, now I don't know how I started that sentence. Let me back up. Reject, I said we're going to reject. Okay, I couldn't remember if I said reject or fail to reject. We're going to reject the null hypothesis if our test statistic, no, I'm not saying that correctly. Yes. Yeah. No, P is the probability, the likelihood of getting a test statistic way out here. That's what p-value is. The probability of that occurring, whatever, the probability of that occurring if the null hypothesis is true. That's what a p-value is. There is a reason that you have to know whether you're dealing with a one-tail test or a two-tail test, because when we tomorrow use the button on the calculator that will calculate the p-value for us, one of the things that we have to put in is whether it's a left tail, a right tail, or a two-tail test. We have to tell the calculator that in order for it to give us the right p-value. All right. If the alternative hypothesis is less, let's say p is less than something, or mu is less than something, or sigma is less than something, if your alternative hypothesis has a less than in it, you're going to have a left tail test. You're going to reject the null hypothesis if your test statistic falls out there in the right or left tail end of the normal distribution. So if the null hypothesis, if you want to assign some words to this slide's kind of short on words, but what you could add is if the alternative hypothesis has a less than, this is a left tail test. That means the rejection region is in the left tail, and we're not going to call it the acceptance region, but the fail to reject region is everywhere else. If your alternative hypothesis has a greater than in it, then it's a right tail test. That would mean that your rejection region is in the right tail, and unless your test statistic lies out there in the right tail, you're going to fail to reject the null hypothesis. If the null hypothesis says something is not equal to, that means less than or greater than, that's when you know you have a two-tail test, and we will reject the null hypothesis if our test statistic is way out there in the left end or way out there in the right end. You remember that problem on the practice test? And if I remember correctly, we didn't have one just like it on the real thing, but on the practice test, we were supposed to find the probability that Z was over here or over here. How did we do that? Find the area in the middle and subtract it from 1. You've already found the p-value, you just didn't know it. P-value is that probability that your test statistic will lie in the red region. All right, go back to XORT. The likelihood of having a baby girl, let's see, the claim. This is a different claim. Consider again the claim that with the XORT method of gender selection, the likelihood of having a baby girl is different from 0.05. Doesn't say less than or greater than, it just says different from. There. Then what is the claim? That's what different from means, anything but. So the claim is that P is not equal to 0.5, and we will reject that if what? If P equals 0.5. Always write your alternative hypothesis first. Which one of those, or what is your alternative hypothesis? Does not equal to, and the null hypothesis, P does equal 0.5. The claim that the likelihood of having a baby girl is different than 0.5 can be expressed, as we did on the previous slide, as P is not equal to 0.5, so the critical region is in both ends. It's a two-tail test. We will reject the null hypothesis if the sample proportion is significantly either less than 0.5 or greater than 0.5. Our p-value would be the area in both tail ends. So earlier we were given z equals 0.321. Let's see. We use the TI 8384 to find that the area to the right of 0.321 is 0.0007. How do we use a calculator to find that probability in the right tail is 0.0007? We're not looking for a z-score, we're looking for a probability. That's normal CDF. I could have typed that for you, I didn't think to. When I say we use the calculator, we use normal CDF 3.21 to 9999. Oh, I know why I didn't type that. Because we don't know the mean and the standard deviation. All right, I didn't say that this was a normal, standard normal distribution, so we can't assume that it is. But if you had given me the mean and the standard deviation, then I would have used normal CDF 3.21 to 9999, comma, mean and standard deviation, and it would have given me this value. That 0.0007 is this area. I don't want to write on the screen here, but draw you a arrow, and this end is 0.0007. So that's the probability that Z is greater than 3.21. What's the probability that Z is less than negative 3.21? Same thing. So what is the probability that your test statistic will be in either of those regions? This plus itself, or this doubled. The p-value is twice the area to the right. So 2 times 0.0007 is 0.0014. That's the p-value for this hypothesis test. Such a small p-value shows that there's a very small chance, a less than a 1% chance of getting the same results that were obtained in the sample if the XSort method had no effect. If the probability is actually 0.5 for having a girl, then the probability of getting that is less than 0.0014. That suggests that when using the XSort method, the likelihood of having a baby girl is different than 0.5. Remember, it was 93% girls? 93% girls is way more than 50% girls. All right. Gosh darn it. Got to speed up just a little bit. So what? We know the p-value. What do we do with it? The rest of this chapter, we're going to decide whether to accept or, excuse me, I said that wrong. We're going to decide whether to reject the null or fail to reject the null by comparing our p-value to our significance level. If you want me to be 95% certain when I reject the null hypothesis, then you compare p to 0.05. If you only care that I'm 90% certain, then you would compare p to 0.1. And here's a this memory tool isn't really useful for me Let me read it and I'll tell you why. If P is low, the null must go. In order to know what that means, you have to, well, no, must go and be rejected. I got that, no problem. But if P is high, the null will fly. Confuses me because I want to go fly away. And that would be that'd be the same as must go. It's like when somebody was trying to teach one of my daughters less than or greater than. No, it's not that. It was my daughter who can't tell left from right at 17. It's it's part of her disability. The less than is the symbol your left hand makes, is a good way to teach somebody that concept of leftness. Well, that's fine unless you have a friend that goes, and then you kill that friend. They've messed up your system forever. Whatever helps you remember. If P is less than alpha, then we're going to reject the null hypothesis. If P is greater than alpha, then we're not going to reject. That will fly does not mean will fly. Or will fly away. It means will not be rejected. All right, let's do a few examples on finding p-values and using them to state the initial conclusion, either reject the null hypothesis or fail to reject the null hypothesis. After today, we're going to use the calculator to find p-values, but today we're going to make sure you understand what a p-value is as it represents area. Number 34 says with alternate hypothesis p is not equal to 3/4, the test statistic is z equals 0.35. Now, the fact that the alternate hypothesis has not equals in it means this is what kind of test, a left tail, right tail, or two-tail test. When you have not equals in the alternate hypothesis, that tells you you're conducting a two-tail test and the z-score is 0.35. So for this p-value, we're looking for the area in both ends of the normal distribution, the area beyond the z-score z equals positive 0.35, and the area to the left of z equals negative 0.35. How do I find a z-score that has, how do I find an area that is to the right of the z-score 0.35 or to the left of the z-score negative 0.35? What function on the calculator do I use to find the area or probability to the right of the z-score 0.35? Well, I have shaded from 0.35 to 9,999, or forever to the right, and that's what we use for an upper boundary, so I use normal CDF. Normal CDF, I have shaded from 0.35 to 9,999. I want that probability or area, and it is 0.363 if we round to 3 decimal places. That area is 0.363. I'm going to go ahead and round to 2 decimal places, 0.3632, which means this area is also 0.3632. Since the p-value for this test statistic is the area in both ends, I could either add those two areas together, or I can just use the area the calculator found with normal CDF and double it. That p-value is 0.7263. In some of the homework problems, this is what you're going to have to do. Find the p-value and then state the initial conclusion. You'll remember from the previous slide, we have to be given some significance level. We were told to use a significance level of 0.05. And for that significance level, 0.72 is much greater than 0.05. The mnemonic device we used was if P is high, that means higher than the significance level, then the null will fly. That means I don't have to reject the null. I'm going to say fail to reject the null hypothesis. Again, fail to reject does not mean to accept. We just don't have enough evidence to support or reject this conclusion or the claim that was being made. So find the p-value, and if p is greater than alpha, then you fail to reject the null hypothesis. If p is less than alpha, then you reject the null hypothesis. All right, on number 35, the alternate hypothesis is p is greater than 1/4. Is that a left tail, right tail, or two-tail test? The greater than symbol pointing to the right means this is a right tail test. And so the p-value that we're looking for is the area to the right of the test statistic we're given. And the test statistic is 2.3. So I'm going to use normal CDF to find the area from 2.3 to 9999. 2.3 to 9999. That probability is 0.0107. And the initial conclusion is based on whether that p-value is greater than the significance level or less than the significance level. With a significance level of 0.05, is this less than 0.05 or greater than 0.05? It's less than. And if p is low, the null must go. We must reject the null hypothesis. And we haven't talked too much about the final conclusion yet. We'll do that in just a minute. But that either means that I have enough evidence to support the claim or to reject the claim, depending on what the claim is. All right, one more. Number 36. The alternate hypothesis is P is less than 0.7777. Is that a left tail, right tail, or two-tail test? The inequality pointing to the left means it's a left tail test. And that means that our p-value is the area to the left of our z-score. We're looking for the area to the left of negative 2.95. So I'm going to use normal CDF. I've shaded forever to the left, so I'm going to use negative 9,999 and say normal CDF, negative 9,999 up to 2.95. Sorry, that was supposed to be negative 2.95. And that probability is 0.0016. Compare that to the significance level of 0.05. 0.0016 is less than the significance level. And again, if P is low, the null must go. We have to reject the null hypothesis. All right, we've done all of the parts of a hypothesis test except for the final conclusion. We've done the middle, which was basically establishing the I think I think I said the wrong thing. We've done the beginning, which was basically establish the null and alternate hypotheses. We've done the middle. We have found p-values. We understand significance levels and how to state the initial conclusion based on whether our p-value is greater than the significance level or less than the significance level. All that's left is for us to learn how to state the final conclusion in terms of the claim, and we'll do that in part B.